Welcome to the talk for X-ray, approximating omnidirectional millimeter wave coverage using an array of phased arrays. I'm Song Wang. I'm a PhD student at the University of California, San Diego. I'm going to start my presentation with the motivation for this work. State-of-the-art wireless networks, including 5G NR and WeGig, have been incorporating millimeter wave technologies to meet the challenge of increasing mobile traffic. Millimeter wave radios usually use phased array antennas to form directional beams to compensate high attenuation loss. However, the high directionality brings two challenges to single phased array design. The first challenge is limited field of view coverage. A phased array has limited field of view, typically narrower than 120 degrees, due to the intrinsic properties of its patched antenna elements. The second is beam management overhead. A phased array has to scan hundreds of beams pointing at different directions to cover its field of view, which incurs huge overhead. This problem becomes more severe when the phased array size is large. To overcome the field of view limitation, without introducing extra beam management overhead, an array of phased array structure, also called APA, has been proposed and adopted by 802.11ay and upcoming BGPPNR. In an APA millimeter wave radio, multiple phased arrays are co-located, sharing the same RF chain, but facing different angles, to jointly cover 360 degrees in azimuth or elevation. Comparing to the single phased array millimeter wave radios, APA can potentially achieve omnidirectional Wi-Fi-like coverage by combining the coverages of each arrays. In addition, the combined coverage may provide more multipath diversities. That is, signals may traverse different paths through reflections, making it easier to save a link under blockage. However, there are fundamental challenges in designing APA millimeter wave systems. The first challenge is joint array beam selection. In APA, the beam management problem is further compounded by array selection, since each array can choose its own beam, or even to be idle. For an APA radio, there are b to the power of p possible array beam combinations, where b is the number of beams and p is the number of arrays. For a typical 8-array AP with 64 beams for each array, it means 2.8 times 10 to the power of 14 combinations. It takes the standard beam searching hours to traverse all these combinations, and it is impossible to select the best combination in real time, where links are mobile and require array beam selection every few hundred milliseconds. The second challenge is multi-array cophasing. The phased array on the same APA node share the same RF chain and transmit the same baseband signals. Due to their relative location and orientation differences, the emitted signals do not necessarily combine coherently at the receiver, causing RSS fluctuations. To showcase this phenomenon, we run a control experiment with two arrays, indexed 7 and 6, on the AP, facing the client direction. We carry the receiver 5 meters away from AP and walk in front of the AP. The figure shows the RSS variations within 100 milliseconds. We see more than 7 dB of RSS loss caused by incoherent signal combination. Moreover, the RSS varies significantly within a short period of 100 milliseconds. indicating the signal coherency is correlated to UE location, and even slight location variation can cause significant link quality changes. To address these challenges, we present a novel system called X-Array, which explores the challenges and opportunities from APA through three major design components. First, we design an optimization-driven array beam selection algorithm to maximize the link quality under the power budget constraints. Second, we introduce a low-overhead dynamic co-phasing algorithm to different transmit arrays so that their signals can coherently combine at the receiver with very infrequent feedback. Finally, we propose a link recovery mechanism that leverages the multi-array architecture to efficiently and accurately find alternative array beams when the strong path disappears or reappears. Next, we introduce the details of each design component. We formulate the joint array beam selection as an offline optimization problem. For a given AOD, the objective is to appropriate the optimal beam pattern to maximize the power towards the AOD direction subject to FCC power constraints. This optimization framework is nonlinear, and the search space is determined by the number of beams and arrays, and can be easily intractable. Hence, we relax the optimization by allowing choosing an arbitrary number of beams on one array. And then we reallocate the surplus beams on one array to its neighboring arrays. The optimization runs one time, and we store the array beam selection into a lookup table with AOD as the key. So how do we know the AOD in the first place? Traditional AOD estimation algorithms, such as the famous MUSIC, require phase information as input, which is unavailable on commodity mmWave radios. Hence, we designed a lightweight RSS-based AOD estimation algorithm. At runtime, X-Array acquires per beam RSS measurement from standard 802.11ad beam searching, and correlate the measurement with the ideal per beam RSS sequences of different AODs to find the optimal match. Using this simple AOD estimation approach, we are able to achieve less than 3-degree error with negligible overhead. One major challenge for APA is to accurately estimate and compensate the inter-array phase offset, the so-called co-phasing vector, to combine the array signals coherently. In commodity devices, phase information is unavailable. We adopt a measurement-driven method to estimate the co-phasing vector periodically. The AP transmits 4 reference signals using the reference array and one side array simultaneously. During the transmission, we apply phase shift values of 0, pi over 2, pi, and 3 pi over 2 to each of the reference signals. We then measure the RSS value of each reference signal. The co-phasing vector can be estimated by applying FFT of the RSS sequences. This whole process takes 0.06 milliseconds for one array. So even with 8 active arrays, the total overhead is still negligible. The foregoing co-phasing algorithm assumes that the AOD information is always available as input. However, the inter-array phase offset varies drastically over only a few milliseconds under node mobility, whereas the AOD can only be updated every 100 milliseconds in order to tame the estimation overhead. We address this challenge using an angular speed-based dynamic co-phasing scheme. Within 2 AOD measurements, dynamic co-phasing predicts the optimal instantaneously co-phasing vector by modeling the relationship between the array steering vector and the UE angular speed. We can then apply the complex conjugate of it to each phase array to cancel out array phase offsets, making the signal coherent. The figure shows the ground truth cophasing vector versus the predicted cophasing rate from AOD estimation every 100 milliseconds. We see that the predicted phase changing rate matches the ground truth near perfectly, indicating the effectiveness of dynamic cophasing. It is well known that the millimeter wave links are prone to blockage. To handle the blockage, we propose a simple concurrent beam swapping scheme taking advantage of APA structure. Upon blockage, the AP loads all arrays with the same codebook to find the best beam index. If any strong line of sight or non-line of sight path exists, then at least one beam will lead to a strong AOD peak. The AP then scans a beam with the strongest RSS on each array to find the best array. This simple design reduces complexity significantly. We implement X-ray based on an off-the-shelf 802.11ad AP. The original AP puts 8 phase arrays on a plane. We reorganize its physical layout and 3D print an antenna stand so that the field of views of different arrays partially overlap, and together they cover 360-degree azimuth. The UE has a single phased array. Both devices compress an 802.11ad network interface card with 2-bit phase shifters plugged in an embedded Linux host. The commercial off-the-shelf network interface card does not provide user with per beam RSS, which is essential to X-arrays AOD estimation and dynamic cophasing designs. Hence, we hack the network interface card firmware, plant a piece of code that copies the per beam RSS values to an accessible memory space. From there, our Python program can safely extract the values in user space, where we implement our X-ray designs. Now we present the evaluation of X-ray. We first validate the accuracy and the effectiveness of X-ray's AOD estimation in 3 different environments. In each environment, we fix the AP and randomly place the clients to 80 locations. We compare 3 schemes: ACO, which is the state-of-the-art AOD estimation design, X-ray, and the scan-only AOD estimation, which simply regards the beamforming direction as the AOD. The left figure shows that X-ray has the lowest average estimation error and the lowest standard deviation, meaning it achieves the most accurate and stable AOD estimation. We then examine the effectiveness of X-ray's joint array beam selection. We compare X-ray with the baseline approach of letting 2 arrays beamform to the same direction to emulate the effect of treating APA as a single giant phase array. The right figure shows that even at 75 miles per hour, the beam coherency time of X-ray remains within one beacon interval of 100 milliseconds, whereas the giant array's beam coherent time is already lower than 100 milliseconds at 45 miles per hour. We then examine X-ray's phase prediction accuracy. We conduct the cophasing experiments by arbitrarily walking along 10 rows inside an office building and repeat the aforementioned point-wise measurement in outdoor open space. As we previously observed, the phase change rate estimated by X-ray shares a high similar pattern with the ground truth. The box plot here further shows the percentile error when we run phase prediction in indoor at 3 miles per hour walking speed, and outdoor at varying speeds from 15 miles per hour to 75 miles per hour settings. We see that the X-ray has an average phase error of 0.57 and 0.44 in outdoor and indoor, which translate to around only 12% throughput loss. Meanwhile, periodic probing phase error are around 2.5 times and 5 times higher, which translate to 18% and 42% throughput loss. To verify whether X-ray effectively exploits the coverage advantage of APA, we conduct experiments with different number of arrays, and by disabling and enabling its design components in both typical indoor and outdoor scenarios. We evaluate the case with 2, 4, and 8 arrays running X-ray, and the case with 4 arrays, but disabling the array selection and co-phasing. The result of indoor scenario is shown in the figure. We see although 8 array achieves similar coverage as 4 array, the areas with high bitrate links is much larger, thanks to array with partially overlapping field of views providing co-phasing gains. Overall, with 8 arrays, X-ray eliminates all blind spots in the room, even for the locations with thick walls. We then compare the overall throughput of X-ray and periodic probing in open space and complex outdoor environment, and conduct the experiments in 5 trials at different locations for each setting. The figure shows that X-ray has a near zero median and 75 percentile throughput gap, and only several outliers in all settings. In contrast, periodic probing suffers from 20 to 57% normalized throughput gap. The experiment verifies the importance of the predictive co-phasing of X-ray under different moving speed. In summary, we have explored APA as a new paradigm to simultaneously improve the millimeter wave coverage and link quality. Our X-ray solution framework builds on the 802.11ad standard and runs directly on commodity devices. Our experiments has verified X-ray's advantages in terms of efficiency, coverage, and the ability to rapidly recover from link outage. For more details, please check our paper. Thanks for watching.